Alright guys, welcome back to another video, and today I'm going to talk about the geometrical applications of differential calculus. So I'm going to assume that you have already studied stationary points, inflection points, and all their theorems to do this standard polynomial question just for reference. So you may be wondering, oh yeah, we can just use factoring and just guess where the stationary points are, right? But this isn't the case. Calculus is a rigorous method that allows you to find the turning points of each function. So remember in year 11 or 10 when you studied the polynomials chapters that you didn't need to find the exact turning points of a function. But in today's video, we will show you how to do it by using a relatively easy example. So first of all, you would do anything like you did before. You would just factor out the x to the power 4 as seen here, and you get your x-intercepts, nothing special. But now that we have learned differentiation, we can just use the power rule, right? And we can just say 5x4 minus 20x cubed. So you may be wondering, what's the point of finding the derivative? Well, the derivative describes the gradient at an instantaneous point, and whenever we find the values of the gradient as equal to 0, we match the definition of a stationary point. So when we equal this to 0, we solve it again, which is x cubed 5x, oh wait, my bad, 5, include the 5 at the front, x minus 4 equals 0. Therefore, it has turning points at x equals 4 and 0. This is called stationary points when the gradient equals to 0. So I hope this was relatively easy to understand because you're just differentiating using the power rule. There's nothing too special. So now that we found px and p prime of x, we can find p prime prime of x because according to the derivative laws, we can keep differentiating a function until it's a constant, right? Or until it's just indefinite 0. So p prime prime of x is just differentiating p prime of x again, which is basically just applying the power rule again. Simple enough. X squared, right? Now you factor it out, 20x squared, x minus 3, right? And therefore, as an inflection point at x equals 3 or x equals 0. These are our inflection points. So this is just the basic geometrical applications of calculus, finding the stationary points and the inflection points. So now you found the x-coordinates of these, we can try to graph the function now. We have our x-intercepts, we have our first and second derivative calculated. So I'm going to clear the whiteboard, but I'm going to review again. P of x equals x5 minus 5x4. This makes it so that we have stationary points at x equals 4 or x equals 0, and inflection points at x equals 3 or x equals 0. So now you may be wondering, how do we graph it now? So now that we have found our stationary point coordinates, we can just draw the coordinate axes, simple enough, and use our x-intercepts first. First, you have to label the x-intercepts, which we can just factor again, x minus 5 for reference. So our x-intercepts will be at 0 and 5. And now, we have a stationary point at 0, so our gradient will just be 0 here. We found our first stationary point, and we have our x equals 4, which you sub in to the function, or if you have a function calculator, you can put in your calculator, which is negative 256. So just place it all the way down here. This is the values where the gradient is equal to 0. So they will just turn back up. So we can just predict that this will have a shape like this. But second, not only do we have the stationary points, we also have the inflection points, which at x equals 3, you can also just sub it in to your function calculator, and you will get negative 162. So around here, like this. This is our inflection point, which changes concavity. Alright, now that we've found the turning points, we can use the first derivative sine table to maximize our accuracy. Remember from the previous video that we used a sine table. This is also really important again. So we're just going to put these values in. And remember that these normal inflection points aren't included in our sine table. We only want to include stationary inflection points. Anyways, we have our stationary points x equals 0 and at 4. So by subbing in the derivative function, you can sub in all these values and you will get something desirable at the end that will help you a lot. So by doing this, we say, what's the values that are less than 0? Function negative 1, right? This will be positive, so therefore the function is increasing, since the derivative is positive if you put it in your calculator. Then, if you put function of 0, you'll get 0. That means the function will flatline. And from 0 to 4, sub in any number that's between them, you will just get a negative value, like this. And then 4, you can just predict already, it's a stationary point. Then any values above 4, the function is increasing from putting in our calculator. So now, we have the first derivative timetable. We have our stationary points and inflection points. Now we can finally graph the function. Well, using calculus proves why an odd degree is always starting from the bottom, right? Because our function is increasing, it can never go from here, because whenever it goes from the positive infinite side, you will always have a function that's decreasing. Anyways, ignore this number that's really big, but you can just draw it here. Stationary point turns, then turns again, and boom, this is your graph. Being exactly precise in our inflection points and stationary points. This is the power of calculus. Instead of just guessing where the stationary points are, a standard year 11 student would probably do something like this. They'll probably guess where it is and just do some weird graph where there's no inflection points and it will look like this. But this is not the case, as we can see with this function here. Also, the reason why x equals 0 is not an inflection point is because this is another special case. I need to talk to you about this special case. The special case occurs when f prime of x equals to 0 and f prime prime of x would equal to 0. Since it's both, and the second derivative sine table would just state that they're both concave up or concave down due to the nature of the turning point, you will have to determine from instead the first derivative sine table and see if it's a relative max or min from that earlier example. That is why sometimes if you have this special case, you have to double check with your first derivative sine table to ensure you're not doing anything wrong. Anyways, let's move on to a harder example where it is not as simple